Right, Bismillahirrahmanirrahim. Last time we looked at IP version 4, right? So the IP layer, and we looked at how the addresses work. And hopefully through the lab you understand a little bit well how these things are going to work together when you have multiple LANs. Okay, so this is essentially the whole idea behind this layer and this chapter, that when you have multiple local area networks, how do they communicate with each other? Okay, you have seen in the lab as well and in the previous lecture as well that as soon as you have two different LANs, you don't worry about the MAC. Okay, and the reason for that is MAC requires by its definition a broadcast initially, and if you're going to broadcast everything everywhere, it's going to be a problem. Okay, everybody agree on this? So if you have 100 devices connected to 100 other devices and you're going to start broadcasting, then it's going to be 100 into 100, 10,000 broadcast messages. Okay, and after every like 5 minutes, so it create congestions in the network, and therefore we separate different local area networks into their own little boxes. And whenever you want to communicate within the box, you have a broadcast, but whenever you want to go from outside the box to another box, one local area network to another local area network, then you don't have a broadcast, and the efficiency of the network or the communication media increases by a lot. Okay, so make sure that you have this thing at the back of your mind, that we are not trying to solve the problem of this lab that you see 25 PCs. No, we are talking about large scale networks, the whole world, and you can imagine there are billions of devices. Okay, so you have to keep that at the back of your mind, that these protocols and these rules are created both for the small scale and for the large scale. In the small scale, they do give you some benefits. Those benefits are not that big, but if you don't have this rule, then in the large scale your network is simply not going to work. Right? So in the small scale, it's the difference between slow and fast. In the large scale, it's the difference between not happening and happening efficiently. Okay, so it's a big advantage. Okay, is this clear to everybody? All right. So we started off with the discussion of our IPv4s, and essentially we looked at how the subnet mask works. Okay, and we're going to continue this same idea. So it's good to remind you of the rule. The rule is very simple. In your subnet mask, you're going to have either a 1 or a 0. It's binary, so it's either a 1 or a 0. All the ones are for the network portion. How do you calculate the network portion? You basically AND the subnet mask with any IP address and you get the network portion. Okay, so that's the basic rule. And even though in today's lesson we are going to look at a slightly different example of how this is done, and the use case where it is used in the real world is going to be different, but the idea is exactly the same. Like the calculation is exactly the same, no difference at all. Okay, the numbers, if you look at them in binary, are going to be exactly the same. If you convert those into decimals, then it's going to look a little weird. Okay, so you have to keep this in mind, that the rule is subnet mask has 1s and 0s. 1s are for the network portion. How do you get the network portion from an IP address? You take it in binary, the IP address in binary, the subnet mask in binary, and you AND it. That's all. Okay, you get the network portion. Then in the host portion, if you have all zeros, the host portion, whatever the bits are, if you have all zeros, that gives you the network address. If you have all ones, it gives you the broadcast address. Okay, and everything in the middle is a possible host address. Okay, so the first one is network address, the last one is broadcast address, everything in the middle is host. So it's as simple as that, but that's all the rule. Okay, that's all the rules that there are. And in today's lesson, we are going to look at a slightly different case study of how to apply these rules, but it's exactly the same thing. Okay, we have a very brief short lesson today, but we want to finish this off. Okay, so let's come back to this. Then we discussed network address translation. If you have public IPs and private IPs cannot communicate with the public IPs, so you need a device in the middle which can create a route from the private IPs to the public IPs, and that device is called the router, which we saw last time as well. Okay, all right. By the way, in this week's lab, we are going to have multiple routers, and you will see how when you connect different routers at the same time in a larger network, what are the configuration changes that you have to make. The rules are exactly the same. You've seen all the rules that you needed. Now it's just a matter of looking at larger and larger, more complex networks so that you understand how at the large scale these rules are applied. The rules are the same. Okay? Okay. So there are some special use IP version 4 addresses. So you may have seen these before, especially if you've taken something like a web course. So this is 127.0.0/8. What that means is there is a network in which the first 8 bits are for the network and the rest are for the host. So this network can possibly have 127.0.0.1, 127.0.0.2, 127.0.0.3, all the way up to 127.255, 255, 254. Okay, so I'm just converting the binary into decimals. Okay, but the point is this is a special type of address. Okay, this is called a loopback address. Okay, it's called a loopback address because it loops back and comes to the same PC that you started from. I'll draw it and then it's going to make sense. So let's say you have a PC over here. This PC has no network card. Okay, it doesn't have a network card, which means it cannot connect to another device. Yes, it cannot connect to another device. Okay, but let's say you want to do development on this machine. Okay, you want to create a server and you want to write applications that communicate the same way that they would communicate to a network device. Okay, so even though you've created the server software, for example a web server on this machine, you want to write client software so that it takes care of the networking, so that later on if you have a server machine you don't have to change the client machine. Make sense? So let me say this. So you are trying to write a server software over here and a client software over here on the same machine. So both the server and the client are on the same machine, but what you want is to write the client software so that it doesn't directly communicate with the server. Why? Because if you directly communicate with the server on this machine, then if later on you move this server to another machine, you have to now change the client as well. Make sense? Because the communication was assuming that you're on the same machine. Okay, so now you have to change the client as well. Well, why don't you create two machines? Because developers, when they're working, they like to work on their own single machine. Okay, when you're working, you have one machine, you want to be able to take the machine laptop, it's a laptop, you want to take it home, you want to bring it here, you don't want to take two machines with you. So you understand the scenario? This is a very common scenario. Okay, so for this purpose, what they've done is they've come up with a special IP address which is called the loopback IP address. So that is going to be assigned to this PC. This has nothing to do with any network device. It's just going to exist. And this network address is going to be 127. It's going to be within this network. Okay. So typically this is 127.0.0.1. Okay. Now this is an IP address. That is a network address. This is an IP address. Do you see the difference? This has a 1 at the end. So now this is a host address. So it's an address which is given to this PC. Okay. So what's the purpose? Now when you write the client software, you are going to communicate with this address and you're going to treat it like any other IP address. So when you are writing the client software, you are going to communicate with 127.0.0.1. But what is this machine? This packet is going to come out and essentially go back to the same machine. So that's why it's called a loop back. It loops back to the same machine. Okay. So now what? Now your server is at 127.0.0.1 IP address. You think of this as being on another machine which just happens to have the IP address of 127.0.0.1. You write your whole client software, you make it work and you do all the debugging and everything. Later on, when you change the server from this machine to this machine, let's say this machine has the IP address of 10.2.9.7. Okay. All you have to do is go into your client and change the IP address from 127.0.0.1 to 10.2.9.7. That's it. That's the only change you have to make in order to enable the server to move. Understand? Okay. So that is why. So the concept of loopback interface is very simple. It's an IP address which is given to the machine. What does it connect to? It connects to the same machine. Okay. So that's the whole concept. The rest of the story is about the why. You have this so that you create networking, essentially a network between this machine and itself. Why? So that you can write software which works on the network and your machine acts like two different machines. Your software acts like it's on this machine and on this machine. It just so happens that physically they're on the same machine. Okay, so your server and client are on the same machine, and if you want to connect to this other machine which the server is on, you just use the 127.0.0.1, which goes back and comes to the same PC or device. Okay, so all devices have this IP address, whether you use it or not. Okay, you can test this by going to your IP config, command prompt, and just issue the command ping 127.0.0.1, and it's going to ping. How is it pinging? Even if there is no connectivity, you can try this in Packet Tracer, by the way. Just create a single PC with no wires, right? Go to the command prompt and ping 127.0.0.1. The ping is going to work. How is the ping working? Ping doesn't know that it's the same machine. It just goes to the IP address, connects to the IP address, sends the packet out, which is essentially inside the same device, and it gets the response and everything is working. Okay? So this is called the loopback address. Primarily, it is used for development on local machines, primarily. Okay? So why don't you use just the normal connectivity? Because if you use non-networking communication, then if you do move to the network, you have to change your software. Okay? All right. So this is commonly identified as only 127.0.0.1 and used on a host to test if TCP/IP is operational. So this is one example. So if, for example, you have some software configuration errors in your machine, for example, the networking software itself, TCP/IP stack, is not properly installed, and you try to ping 127.0.0.1 and you cannot even ping 127.0.0.1, that means that there is something really wrong with your networking software. Okay? Not your software, not your client, not your command prompt, but the actual operating system. So this is hardly ever the problem. But as I told you, this is not the motivating use case. The testing is not the motivating use case. The motivating use case comes from development. Okay? Is this clear? So those of you who've taken a web course, you would remember that we used to write localhost / and then our something.php. It was going from the browser to the server, and it acted like a website. Okay, so it acts like a website even though it's on the same machine. The reason for that is localhost. When you write localhost, the domain localhost, it's not the domain, but you can think of this as a full name. So this domain resolves to the IP address of 127.0.0.1. You remember DNS? We give it a domain name, it gives you back an IP address. So the operating systems, almost all operating systems, all operating systems resolve localhost to 127.0.0.1. So you can just use localhost instead of 127.0.0.1. Make sense? Right. So the name localhost resolves to 127.0.0.1, which is a loopback address which is used to communicate with the same device, which is why it's called a loopback address.
What is TCP/IP?
So TCP/IP is that full stack, OSI model and the TCP/IP model.
Oh, so there's something in
Yes, of course, you're going to have some softwares in your operating system which
in the same Packet Tracer, and they sometimes have TCP and sometimes UDP.
That we're going to come to. That's on the next layer. That's on the transport layer, layer 4. That we'll do when we get to transport layer. That will come to. Yes, good question, but I cannot answer that right now. Okay, so we will come back to that. Okay. There is also another address called linked local address. So I'll tell you what this is. It's hardly ever used, so it's not very important. But the idea of linked local address is, if you are on a network, let's say there are 3 devices on a network, and you have not statically configured the IP addresses of these networks, of these devices, and you don't have a DHCP. Okay? No static configuration, no DHCP. That means your devices don't have their IP addresses. Okay? But there is going to be an address given to the interface which is kind of like the default. Okay? So it looks like this, 169.254. This thing over here. So it's going to have 169.254. Some unique value over here. Okay? Understand? So you can think of this as just some IP address which is given by default. If no other IP, if it's not static, if it's not DHCP, then some address is just given. Okay? Why? So the reason given in slides and books and all the material is so that you can communicate with the device. Nobody actually does it. Right? You need to give an IP address either statically or through DHCP. So nobody uses linked local address, but it's there just so you have an IP address assigned even if you don't give it statically or with DHCP. Okay, so it's not very important. I'll tell you what you need to know with linked local addresses. Linked local addresses are those addresses which are assigned to an interface if you don't statically give it an IP address and you don't have a DHCP. If both of them are missing, then the address which is given to that interface is the linked local address. That's all you need to know. Okay? Is this clear? Yes? No? Awake? Sleeping? Okay. All right. So, I actually wanted to get rid of this slide because it's useless, as you can see at the end. Nobody does it anymore. But it's a terminology that you should know, even though nobody uses it. Right? Because people who don't actually work practically with networks expect you to know this. Right? And they're going to ask you in like job interviews and stuff. So you need to know what this is, even though nobody uses it anymore. Okay. So this is called the creating classes in IP addresses. So your IP addresses can go from all zeros to all ones in 32-bit. Right? So all zeros to all ones. That's what the possible values of IP addresses are. When the networks were initially created, they divided all of this thing, all of the possible IP addresses into 5 or 6 different classes. Okay. So, for example, class A started from 00002 0000/8 to 127.0.0.0/8. Okay. So now you have to be able to read this and kind of understand what it means. It means an IP address in which the first portion, first octet, can go from 0 to it's /8, right? So it can go from 0 to, right? So the first 8, right? So it can go from 0 to 255, but the range of class A in this is up to 127. Okay. So for example, you have the IP address 10.2.9.7. Okay. So let's make this 12. 12.2.9.7. It is in class A. Why? Because if you take the /8 of this, you get 12.0.0.0, and it is within this range from 000 to 127. So it falls in class A. Okay. Let's say you have 154.2.9.7. Okay. You take the /8 of this, you get 154.0.0.0. Okay. Does it fall in this range? No. Does it fall in this range? Right. So 154 is in this range, so it's a class B address. Okay. So that's all we're saying. Take the whole thing, divide it into different ranges. These ranges are not equal. It's not important for you to memorize these ranges. You just have to know that the all possible IP addresses, if you sort them, they are divided into classes. The first class is very large, the second class is slightly smaller, and then smaller, and then smaller, but it's not important to understand that. It's just some ranges which have been defined, right? And traditionally, it used to be that class A had its own specific purpose, class B had its own purpose, class C had its own purpose, and so on and so forth, okay? So these are called classes of IP addresses, okay? So you have class A, which has this range, class B, class C, class D, and class E, okay? The point is, nobody uses it anymore, okay? So these are called legacy classful addressing. Now you have classless addresses. So you had quite complicated rules about what you can and cannot do with these classes. They're no longer used, but you do need to understand that there used to be a thing called class A, class B, class C, class D, class E, so that if somebody asks you, for example, in a job interview, you know what they are, right? So you just need to know the terminology. It's no longer used, okay? People actually spend like quite a lot of time discussing this, because if you have this and you have to explain the numbers, it takes a long while, but it's useless. In practice, they are no longer used, okay? Just clear? Okay. So now you have classless addresses. So what happens is, whenever you have such a large scale global environment, you need to have somebody to basically take care of the root level. I'll tell you what that means. So if you remember, we said that we are going to have this lab over here. We are going to assign the IP addresses ourselves. We can give it any private IP address, right? So let's say 192.168.0.5. I gave it to this PC. Okay, and I have the whole thing, all of the IP addresses are given. Over here, I have a router. This router has two portions. One is going to be 192.168.0.1 and the other is going to be 17.2.9.5. Okay, I gave it a public IP address. You remember that public IP addresses are unique across the whole world, right? So how do I ensure that nobody else in the whole world has actually assigned 17.2.9.5 to their router? See the problem? It has to be unique because otherwise communication is not going to work. But if it has to be unique, I have to know that nobody else in the whole world is using it. Agreed? So do I go and ask everybody in the world? No, obviously that doesn't work. So what happens is there is an organization which is Internet Assigned Numbers Authority, IANA. Okay, so it's this authority which actually you have to go and like pay them a small fees and something, and they give you an IP address. They actually give you ranges of IP address that you can use, but you get the idea. Is this clear? So that's all this slide is saying. It's saying that there are different organizations and different sub-organizations, and because the whole world is involved and some governments don't trust other governments, and it's a big mess. It doesn't affect us. What it means is that there is an organization which is going to give you the IP address that you can use. And they are going to keep track of which IP addresses are in use, which are free, and which are whatever. Is this clear?
Yeah,
yes.
They give us the IP address as a single or from a fax or phone fax?
Yes, they give you a range. Essentially, you purchase a block. It's called a block. Okay, so block is a range. So you say, I want 17.2.9.5/24. Okay, so you get that whole range. Was that the question? So you don't get one single IP address, you get a whole range. And for example, if you have 15 routers, you can give one to this and one to this and one to this. And it depends on how large of a block you purchase. And the larger the block, the more it's going to cost and stuff like that. Okay, for example, Amazon has like a whole data center with thousands of machines. So they cannot work with like 2 IP addresses. They need to purchase more. Okay, is this clear? But do you understand the problem that now you have IP addresses which are being given to the whole world and you have to keep track of this? And even though it's 32-bit, but the possible number of values that you can put in 32 bits, right? So that's a good example. Go and search for this. That what is the maximum number of, forget about private addresses, like include those as well. What is the maximum number of unique IP addresses you can have in a 32-bit space? That's all the possibility, right? 32 bits. That's what an IP version 4 address looks like. So try to find out how many exact IP addresses there are in the world. Okay? And you have to remember that, for example, I am Amazon, I wish, but let's say I am Amazon and I own Amazon. So I'm going to go and purchase a block. Okay? I have money, I don't care. I'm going to purchase a very large block. I'm going to use like 70% of it, and the rest of the 25% is assigned to me, even though I'm not using it. So it's being wasted, but it's in the list. So it's kind of used, even though it's not really used. So there is a lot of wastage as well. See the problem? So even if you count the maximum number of possible IP addresses, that's not sufficient. On top of that, there is going to be wastage as well. And on top of that, you have some private addresses as well. And you have some other stuff. So the maximum number of IP addresses that you can have is limited. And turned out we ran out of these. These were finished like 10 years ago. We don't have any more IP addresses. People have bought them, and now if you want a new IP address, you can't have it. See the problem?
So what can you do?
Next chapter. But I just wanted to introduce that chapter because this introduction goes over there, but here it makes sense. So, but you see the problem? What's the problem? No more IP addresses. Why? Because everything is connected now to the internet. Yes. So that's the whole. So that's a good question. So we've been doing IP, right? And now I'm saying that it's not used, it's not available. The point is, number one, it's still used. So private addresses you can still use, which is what we deal with on a day-to-day basis. The public addresses, that is exactly why we created that whole layer thing. The first 2 layers don't care about IP addresses. The top layers don't care about IP addresses. It's just this layer, okay, which this problem affects. Everybody else doesn't care. Why? Because they don't look at layer 3. That's why we created layers. Okay. Now you have layer 3, and layer 3 has a problem. You just go and fix layer 3, which we are going to do very easily in the next chapter. Okay, in the next layer when we do, not in the next layer, in this layer when we do the next chapter, you're going to see that we solve this problem by changing just a very small thing, and everything else that you've studied up until now, it doesn't get affected because it was not looking at the IP address anyway. Make sense?
Yes.
That's the motivation behind creating all those 7 layers, all those 4 layers. Why? Because if something breaks, you just fix that. You don't have to fix everything. Make sense? Okay, good. So we're going to fix this problem in the next slide set. It's not a big problem. It seems like a huge problem, but because this thing was structured so well, the solutions that were created, so these problems have been solved by some of the most brilliant computer scientists in the world. Okay, so because they were solved in such a way that they were future thinking, when this problem came along, it wasn't that easy. But looking at the scale of the thing, the whole world faces this problem. The solution is going to look to you to be very simple. Okay? It took a while to come up with this solution, and there were issues, but the solution is going to be quite straightforward. Okay, I can actually tell you what the solution is right now. So just go from 32-bit to 64-bit. Now you have more addresses.
So now there is an IP address for 64.
Yes. Okay, but we'll come to that. And you cannot just go ahead and change it. Why? Because the whole world is using it. And you cannot tell the whole world to shut down their computers for one day until we upgrade. So you have to take care of other problems with it. But the solution itself is simple. Okay, we'll come back to this later on. Okay, anyway. So, so same problem as before. So let's forget about IP addresses. For now, you have IP addresses. Okay, you're doing private addresses. So let's say you have when I started today's lesson, I actually gave you this introduction, but I'll say this again. So you have a local area network which has 100 devices. And one device wants to communicate with one other device. It's just these 2 devices, all the other 98 are asleep. But still you have to send a broadcast out to all 100. The other 98 are going to reject the packet, but the broadcast still goes out. Then device 3 wants to communicate with device 4, you get another 100 broadcast messages. 99 get ignored and 1 gets a response. So all of this traffic is going out for no good reason. Okay, so what do? This thing, when you send out a broadcast, all the area, logical area, or all the range, or the PCs, or the devices, where this broadcast is sent, or where a broadcast reaches, is called the broadcast domain. Okay, so the name is kind of weird, but that's what it means. If you send out a broadcast, all the devices where this broadcast goes is called the broadcast domain. And you already know that a broadcast domain is cut short or stopped by a router or a gateway. Okay, you know this. We're just giving it a name now. Okay, so when you send out a broadcast, all the devices where it goes is called a broadcast domain. Okay, so if you have a very large broadcast domain, now we can say it technically. If you have a very large broadcast domain, a lot of information or communication is wasteful. You're wasting the network media. You're sending out unnecessary things. So let's say you have 100 devices, you are going to have 100 by 100 communications going on. If you reduce this to half, you are going to have 50 by 50, which is what? 2500. So you've gone from 10,000 to 2500. That's a 40 times speed up by reducing the number of devices by half. I hope my maths is right. Yes, right? It's a huge difference. If you reduce this to 10 by 10, it's going to be 100. So if you reduce this by half, by 5, you get 250 times, 25 times speed up. But you see the benefit of reducing the broadcast domain? Okay. So why don't we just keep everything at 2 PCs in one broadcast domain? Because then you have to do all the configuration. You remember, you need a switch, and then you have these devices, and then you need a separate DHCP for one LAN. So if you have a very small broadcast domain, then human effort is required to maintain it. Right? For example, if you have 1,000 branches and in an organization, then it's going to create a lot of problem for you. See the problem? Yes or no? So if you have this thing as a separate broadcast domain, and this thing as separate broadcast domain, and this thing as separate broadcast domain, then you need a DHCP for this, and a DHCP for this, and a DHCP for this. Okay? So you have to create a balance between these two. Okay? So how do you do that? You do that by introducing what is called a subnetting. So this is the problem with the broadcast domains. The solution is to reduce the size of the network to create smaller broadcast domains, and this process is called subnetting. So subnetting, because you have a network, okay, and you create a larger network, for example, this whole university, and then you create smaller networks within that, so sub-networks. So this process is called subnetting, and this is where the name subnet mask comes from. Okay, so nothing new. It's going to be exactly the same thing. We're going to have a subnet mask which is going to define different networks. Okay, same idea, no new rule. So for example, you have the network address 172.16.00 by 16. What does that mean? It can have hosts which go from 172.16.0.1 all the way up to 172.16.255.254. Everybody agree on this? I'll say this again. 172.16.0.1 is the first host in this network, and 172.16.255, so all ones there, and 254, all ones except the last one in the final octet. Okay, so these are all the possible combinations. So it's a huge number of devices. Okay, everybody agree? Okay, so it's a very large number of devices. So 255 just for the last 7 bits. And then as soon as you introduce one more bit, it doubles. And then one more bit, it doubles. And one more bit, it doubles. Okay, that's what happens when you add another binary bit, right? So 1 goes to 2, 2 goes to 4, 4 goes to 8, 8 to 16, 34, 64, it kind of explodes. So this is a very large number of devices. So your broadcast domain is very large. What you do is you divide it into 2 subnetworks or subnets, 172.16.00/24 and 172.16.1/24. So now these are 2 separate networks. One is going to be this guy over here and one is going to be this guy over here. So in this network, the possible devices are 172.16.1.1 all the way up to 172.16.1.254. This is the first network. This is the second network, and the first one is going to be 172.16.0.1, 172.16.0.254. Agreed? What has changed? This was /16, this is /24. And this guy got a 0 over here, this guy got a 1 over here. So now the network portion of this one, 172.16.00/24, is 172.16.0. Okay, and the network portion of 172.16.1.0/24 is 172.16.1. Now these are 2 different networks. Again, same rules, no new rule. Agreed, everybody? These 2 are called subnets. Yes.
The first address, isn't the network portion only 172.1.6?
Yes. So that was the original network. We took a portion of it and we said this thing is now a subnet, and the whole rules of the networking and the broadcast and IP and router and everything applies to this guy as well. But now it's a smaller broadcast domain. The broadcast domain has gone from, I don't know, millions to just 255. Okay? Make sense? Okay. So now instead of having, so this diagram doesn't do it justice. So this would probably have been like fill this whole thing with devices. Okay, fill millions of devices over here. And this thing is going to be just 255 devices over here, 255 devices over here. And why is it good for us? Because we can still use the 172 IP address. Okay, we can still use that, but now we have a smaller broadcast domain. Make sense? Okay, let's see a couple of examples and then it's going to make sense. So for example, you can have subnets on an octet boundary. What does that mean? It means, let's say your original IP address was /8. So this was, let's say, let's say, get rid of this. So let's say this was 8.17.2.5. Okay, this was /8. Okay, so if this was /8, this would be its subnet mask, and this whole thing is going to be network portion, and this whole thing is going to be the host portion. Okay, so how many hosts can you have? This is the number, 16 million. Okay, how? Because 2 raised to the power 24. Each bit can go 0 or 1. So you calculate the maximum number that you can represent using this. That is 16 million. 16 million, what is that? 777,216. That is the number you get when you get 2 to the 254. But the maximum number of hosts is 16,777,214, not 216. Why?
The
The first and the last are reserved for network and broadcast. Good. Okay. So this is how you do the calculation. Okay. So this is where people like spend a lot of time trying to do this calculation. But if you understand the rules, it's very simple. How many bits for host? What is the maximum possible number with those bits? This is the maximum possible number. Okay. Forget about the first one. Forget about the last one. This is the number that you get. Okay. For example, if you have for the host portion only 5 bits. Okay. So let's say for the host portion you have only 3 bits. How many possible hosts can you have? So first you do 2 raised to the power 3, which is 8. Okay. So from the 8 you remove the first one and the last one, and so this is 8, but number of hosts is 6. Okay. Make sense? So 2 raised to the power number of bits for the host, calculate that, and minus 2. So that's the number of hosts. So why is this important? If you look at a lab and you see that in a lab, we are generally going to have we're not going to have more than 100 devices in a lab. We know. Why? Because we know our organization. We know that in this organization, in a single local area network, we're not going to have more than 100 devices. So we create a subnet so that, let's say, instead of 100, we make it very, very generous and we say we can have 200 devices. Okay? So you give so many bits to the host so that it can fit 200 devices. Make sense? So you give it, let's say, 8. And 8 can go from 0 to 255. Okay? Do you understand what I just did? We're trying to figure out how many bits to give to the host and how many bits to give to the network. Because remember, if we give too many bits to the host, the possible number of hosts is very large, which means the broadcast is going to be very large. Broadcast domain is going to be very large. So you want to reduce the broadcast domain as much as possible. So maybe 255 is too much. We said maximum we are going to have 100 devices. Okay. So how about we, instead of giving it 8 bits, we give it 7 bits. That means we can go from 0 to 127. Okay. So the maximum devices we can have is 125. Make sense? So we give 7 bits to the host. Make sense? So that is the decision which you as a network administrator, as a network designer have to make. Okay. When you're sitting down, you have to decide how many bits are going to be for the network. But for ease of use, generally what we do is we either take it as 8 or 16 or 24. Okay. So even though I can go with 7 bits for the host, it's just easier for me if I just pick 8 bits. Okay. Make sense? Okay. On the other hand, there might be a local area network in which you can have thousands of devices, right? So it might be difficult for you to imagine this, but if I tell you, then you will think of this. For example, there is a data center of Google. Have you seen a data center? Go and search for a data center picture. You can find it. It's full of racks. There are no screens. It's just server. So you have 10 servers on one rack, and you have hundreds of servers sitting here, and then you have to cool them and all of that. So that is what a data center is. So in that, a local area network may have thousands of devices. Okay, one local area network may have thousands of devices. So that network engineer cannot use 8 bits because 8 bits simply does not have sufficient number of devices. They need more devices in one local area network. So they're going to probably have to use something like /16, which gives you 65,000 devices. Okay, but 65,000 is too much. I need like 3,000. So maybe I can go somewhere in between. So instead of /8 and 16, I can do, so instead of /16 and /24, I can probably say like /20. Okay. It's going to depend on the actual numbers. You have to do the calculation. It's not very important to do the calculation. You have to understand just this example over here. Right. So simple examples, if you can do, larger numbers are the same idea. Okay. Make sense? Okay. So what does it mean if you create a subnet on an octet boundary? It means that the network and host are separated on one of the octet boundaries, as the name suggests. Okay. You can also have subnets not on the octet boundary. For example, you can have, instead of /8, you can have /9. What that means is this is also going to be a 1. Okay. And that gives rise to something like this. So for example, if you have 10.0.0.16, it's going to have ranges from 10.0.0.1 to 10.0.255.254. Hopefully this makes sense now. It's /16, so the other ones you turn them into ones and you get the possible host. Okay, but if you change this to 10.100, so then this gets this. But let's say instead of 16, you change this same thing to 24. So same 10.000/16, 10.000/24. What's the difference now? You can go from 10.001 to 10.00254. And the possible number of devices now over here is just 254. Well, actually 253 because, no, 254, yes. Make sense? Right? So here the possible number of devices is 16 million, not 16 million, 65,000. And here the possible number of devices is 254. You can also, instead of /24, you can go to /25. And that's as simple as this. So this portion over here is the network portion. Exactly the same calculation. But the problem now is if you convert it into decimal, it's going to look like this. Subnet mask is 255.255.255.128. Okay, it's in decimal it looks weird. In binary it makes complete sense. Is this clear? See the subnet mask in binary first. When you see it, you understand it. If you convert it into decimal, it's going to look weird, something weird like 192. Where did this 192 come from? It came from these 2 bits. That's just what this thing looks like in decimal. Okay? People get confused because they try to do these calculations in decimal. And if you do them in decimal, then it's confusing. Okay? For example, if I ask you for this one, what is the first host that you can have? So it's very weird. It's going to have 128 plus 1. Okay? Because 128, this bit over here is going to be 1 because of the network portion, and then this bit you are going to turn into 1 for the first host. So it's going to be 129. So it's weird. Okay? But the rule for the gateway is exactly the same. Look at the subnet mask. Apply it on ending it with the whole IP address. Gives you the network portion. You take the network portion and you take the host portion and you take just the final bit of host portion to 1 and you get the first host address, which is generally given to the gateway. Same rules as we did earlier on over here. Where did we do these rules? So this rule over, exactly this. If you understand this, it's exactly the same procedure, exactly the same rules, even if you don't stop on an exact octet boundary. You can go to /9, /10, /11, /12, exactly the same thing. Is this clear? Any questions?
2, 4, 8, 16, 32 of subnets. What does that mean?
Where? On this slide?
Number of subnets.
Number of subnets. Right. So, for example, if you have the whole network, which is this, it's not important at the moment, but I'll tell you. So, let's say your this whole thing was 10.0.0. Let's say. So let's get rid of this. So 192.168.5. Let's say 0/24. Okay. This was your original network. You say this is a very large broadcast domain. I want to split it. Okay. So you change this /24 to /25. Okay. So what that means is this thing over here can either be a 0 or a 1. The remaining thing is exactly the same, right? 24 is going to remain the same. The 25th bit can either be a 0 or a 1. So that means if it's a 0, it's one subnetwork, because now you have this in the network portion. If it's a 0, it's one subnetwork. If it's a 1, it's another subnetwork. So you get 2 networks, each with a smaller broadcast domain. Make sense? Okay. So if you go from /24 to /25, you can create a maximum of 2 subnetworks. Why? Because that's the only bit you can change. But if you can change 2 bits, then that means you can have a subnet with 00 in the network portion. You can have a 01, you can have a 10, or you can have a 11. So now you can have 4 subnetworks. But on the other hand, each subnetwork, it can only possibly have this many devices, which is 62. Right? So it's a balance between how many subnetworks you can create and how many devices you can have in one network. Because at the end, the IP address can only be 32 bits. Make sense? So this subnetwork, number of subnetwork portions is not all that important, but you can calculate it using this. Okay. So if I tell you that a network is /24 and I'm converting it into /25, how many subnets can I have? I've only added one bit for the network portion, right? And that bit can be either a 0 or a 1. So 2 subnets. And how many hosts can be in this thing? You have 7 bits left for the hosts. So you do 2 to the 7. And whatever you get, minus 2, you get this, 126. So 2 to the 7 is 128. Minus 2, you get 126. Over here, 2 to the 6 is 64. Minus 2 is 62. 2 to the 8, 2 to the 1, 2, 3, 4, 5. 2 to the 5 is 32. Minus 2 is 30, and so on. Okay? Make sense?
Doctor, all this calculation just to determine the number of hosts?
Yes, because when you're designing a large network, it's important that you balance the broadcast domain versus how much effort you have to put in for the config. If you have 5 subnetworks, you have to configure 5 subnetworks. You have to give it a DHCP and you have to like create a router in between each of this. So it's effort on your part. But if it's too large of a subnetwork, then there is a lot of wastage. So even though you're relaxed, but the network is slow. So you have to figure out how much effort do I have to put into my job and how much is it worth that the network remains efficient. Okay? Make sense? So if you have, so let's say if you have 64 number of subnetworks and 2 hosts, there is absolutely no no wastage of broadcast because it's just 2 devices. But now you have to configure 64 subnetworks, 64 routers, 64 DHCPs, 64 switches. You have to take care of all of that. So it's very difficult for me. On the other hand, if you have just 2 subnetworks, now you have to do only 2 routers, only 1 router because it's 2, right? You have to create like 2 DHCP servers, but the broadcast domain is 126. So each thing is going to be very large and there is going to be a lot of wastage. So you have to figure out according to your needs, which one of these you want. That is why you need to do the calculation. How many hosts do you need? For example, over here, the 30 kind of makes sense because it's unlikely we're going to have more than 30 systems over here. Let's say we can have 30, so let's go with the 62 one. So we should use /26 over here in this lab, which has like 20 or 30 PCs. Make sense? Okay. Any other questions? Bismillahirrahmanirrahim. In this lab, we are going to connect multiple routers together. And if you recall, that is going to allow us to create multiple LANs and all the LANs are going to be connected with each other. And you will see how you can then go ahead and scale this up to infinity. So this lab and inshallah in a couple of labs, you will have all the requirements done for creating a very large scale network. So right now what we're doing is we have 3 labs and 3 LANs, and each of these LANs is connected to a router over here. Okay, so we're going to start off with this position because you already know how to do this. You go ahead and place 2 PCs and a switch and a router over here. This router has to be a specific version, so this has to be 1841. So if you go to network devices and routers and scroll to the right, you will see 1841 over here. So make sure that you use this router, because we are going to make some modifications to the hardware of this router and all the other routers may or may not work. Okay, so just to make sure that it's easy for you to follow along with me, make sure that you are using the router model 1841. Okay, anyway, so you place these over here and I've added some information over here to show you what kind of IP addresses we're going to be assigning. So this whole network is going to be 192.168.1.0. This network LAN is going to be 192.168.2.0. This is going to be 192.168.3.0. And the objective is to be able to ping from this PC over to this PC and to this PC over here. Okay. So in order to do that, obviously we need a gateway because we want to go outside of our LAN. So this router is going to be our gateway over here. So this thing which is connected to fast Ethernet 00 is going to be our gateway for this LAN. So let's bring this down over here so that it's clear that this interface of the router is 192.168.1.1. I have not made any configurations for IP addresses. I'll do that during the recording, but these notes are there just to remind you that this is what we are supposed to do. Okay, so let's go ahead and first modify the router for the requirements that are necessary. So in order to do that, we're going to go over here and first make sure that you understand the objective. We want to connect this router to this router and this router to this router. So for this, we are only going to need 2 interfaces. This router has 2 interfaces, that's fine. But this router is going to need 3 interfaces, one to connect to its LAN, one to connect to this router, and a third one to connect to this router. So this router has only 2 interfaces at the moment. What we need is to have 3. So for that, we are going to go to each of these routers. So click on this, go to the physical tab, use this power button to turn it off, and then insert this module, which is WIC2T. So insert this over here. So before going and doing that, you can go to the config. All right, so I'll show this to you in another router. So for this router, they're all the same routers. So if you go to config, you will see that you have only 2 interfaces, Fast Ethernet 00 and Fast Ethernet 01. We need another one over here. Okay, so we go over here. This router is turned off. The first router, router 1, you take WIC2T and place it over here. Then turn the router on. Okay, so when you turn the router on, it's going to take a little bit of time to basically boot. And if you go to the CLI, you will see that this thing is happening over here. And once this is done, then the router would have booted properly. Okay, so when you see this system configuration dialog, then the router is booted. You don't have to do anything over here. Go back to the config, and now you will see that you have 2 more interfaces over here, which is serial 010 and serial 011. Okay, so a serial connectivity is a different type of cable, a different type of connector. We are going to use these over here. Okay, let's do this again for the router 2. So click on the router, go to the physical tab, turn the router off, take WIC2T, place it in one of the free slots, and turn the router back on. Okay, go ahead and close this. Go to the third router, turn the router off, place the WIC2T, turn the router back on, and then go ahead and go to the CLI to make sure that this is done. Okay, so we can hit fast forward to make this done. Okay, so now we are going to connect these routers with each other. So for that, we are going to go over here and pick a different type of cable, which is this cable over here. So this is serial DTE. We're going to take this cable and connect it to the serial 010 over here on this router. And because it's a serial cable, it's not going to fast Ethernet, but into serial. Just think of this as a different type of cable. So instead of the RJ45 connector, it's using the serial connector. Okay. Similarly, over here, we have another serial, which is why we inserted WIC2T and connect this to the serial 010 over here. Okay. So now you have to make sure which ports you have connected this to. This one is connected to the first serial. This one is connected to the serial 010 of router 2, and then serial 011. Okay, so you have to make sure. All right. This router over here has 2 interfaces. So the first interface, which is Fast Ethernet 00, that needs to have the IP of this gateway. Okay, so this has to be 192.168.1.1. Okay, and the subnet mask should be 255.255.255.0. You do that and you close this. So we're going to do this slowly. We go to the PC, we go to the config, we set the Fast Ethernet 0 to 192.168.1.101, which is the IP address. We set the subnet mask. We go to the settings and we set the the default gateway to 192.168.1.1. So this is our gateway, this guy over here. Okay, so this is done, but we need to turn the Fast Ethernet 00 port on. Close this and then fast forward until everything is green. Okay, so this LAN over here is now done. Let's make sure that we can ping our gateway by going to the desktop, going to the command prompt and saying ping 192.168.1.1. You can do the ping, then it's fine. If you cannot, then go ahead and fix this until you can get the ping. All we did was set the IP address and gateway of this guy, set the IP address of this interface, which is Fast Ethernet 0 for this router, and we are going to do something very similar over here. So go to the router, go to the config, Fast Ethernet 00, give it the IP address of 192.168.2.1, give it the subnet mask, make sure that the port is on. Go ahead and close this. Go to PC2, go to config, go to the Fast Ethernet 0, give it 192.168.2.101. That is the IP this PC has. Give it the subnet mask. Go to the settings, set the default gateway 192.168.2.1 because it's this router over here which is our gateway. We don't need the DNS server. Go ahead and close this. Fast forward until everything is green. Again, go over to the router, go to the config, go to Fast Ethernet 0, 192.168.3.1, subnet mask, make sure that the port is on, go to PC, this guy over here, config, default gateway is 192.168.3.1, the Fast Ethernet 0 is 192.168.3.101, subnet mask, and we should be done. Okay, so everything is green over here. These are still red because of two reasons. Number one, the port is off. Number two, we have not given them IP addresses. Okay, so we are able to ping from this guy to this guy. So now what we need to do is we need to configure an IP address for these two ends of the cable. Okay, so which means the first serial port of this guy and the first serial port of this guy. Okay, now because this whole thing is one local area network, and this half of the router and this half of the router, so this portion over here and this portion over here, so the stuff which is connected on this wire, on the two ends of this wire, this is a different network, so we have to give it a different network address. Okay, so I'm going to tell you what the network address is. So serial 010, go to this, give it the IP address of 11.0.0.1, or let's call it 11.0.0.2, and the subnet mask is 255.0.0.0. Now generally you would give a public address. If you recall the rules of the public and private addresses, this is a public address. The routers which are connected, the router interfaces which are connected to other router interfaces generally have a public IP address. Okay, so we are giving it a public IP address. For now, make sure that you give it the same IP version 4 address that I'm using so that you don't get confused. This is going to get slightly complicated in just a minute. Okay, so for this first port of serial, we want to give it the IP address of 11.0.0.2 and give it the subnet mask of 255.0.0.0, which means it's on this network, and we are going to turn it on. Okay, so let's go ahead and close this. Let's make sure that we put a note over here so that we don't mess this up. So this is 11.0.0.2, this thing over here, this is 11.0.0.2, this thing over here, so the first serial address of the second router. So these two, this right half of router 1 and left half of router 2, this is supposed to be one network, which means the IP address of this interface should be on the same network as this one. Okay, so that they can communicate with each other just as you communicate on a LAN. It doesn't matter if it's a public address, the rules are exactly the same. So if this was 11.0.0.2, you have to pick an IP address over here which is on the same network. So I'm going to pick 11.0.0.3 just to make things simpler. Okay, make sure that this is turned on, and you will see that these two have both turned on. I'm going to add a note over here because otherwise I'm going to mess this up. So 11.0.0.3. Okay, so we have this thing over here. Now this is done. Let's go ahead and try to communicate now with this thing over here. So remember, this is an interface. It has an IP address. You can send it a ping. So let's go ahead and try to do that. So come over here, our configuration here. So let's try to ping 192.168.1.1. So this is the first thing over here. So let's see if we can ping this. We can. So it's fine. Hit Control-C to stop. Then go ahead and try to ping this interface. So even though it's the same device, we want to make sure that we can go from over here to this guy over here. Okay, so let's see. Ping 11.0.0.2. So because it's the same router, the router can send information from 192.168.1.1, this interface to this interface. We're good. But if you try to ping this guy over here, 11.0.0.3, let's see what happens. So ping 192.168, so 11.0.0.3. So let's try to ping that. What's going to happen, let's go into simulation mode because this you need to see. We are going to hit enter over here. An ICMP packet is going to be initiated over here. Okay, so this is the ICMP packet. It's going out. The source is 192.168.1.101. The destination is 11.0.0.3. We are going from our MAC address, this guy's MAC address, to this MAC address over here. Okay, you can verify that. Let's go ahead and close this. Let's move the packet. Packet goes out to the switch. Packet goes to the router. Fine. Okay, so let's go ahead and click on this. So what does it say? It got the packet. The routing table finds a routing entry to the destination IP address. Okay, so let's go ahead and move this. It gets to this point over here and it's rejected. Okay, so it got to 11.0.0.3, but then it has nowhere else to go. See, the ICMP process to echo by sending ICMP type to echo, and what it's saying essentially, you can read through this. What it's saying is, now I'm trying to send a message to 192.168.1.101. You are able to send the ping to this 11.0.0.3. That's fine, but the Problem is now you have to send a response back. So it has to be a PONG. So a ping has a PONG. A response has to be generated by this 11003, which has to go to 192.168.1.101. But this router 2 sitting over here, does not know where 192.168.1.101 is. This router knows. Why? Because it's on the same network. So this interface knows where 192.168.1.101 is, but this guy doesn't. Okay, it doesn't matter that the packet came in from here. Now it's a new packet, and if you're going to send it from here to 192.168.1.101, you have to know how to send it, and we haven't told this router that. Okay, so remember this. This router does not know where 192.168.1.101 is. Okay, so let's go ahead and close this. This is going to mean that we are going to get an error over here. So let's go ahead and go back to real time, and you will see that it's going to let's run this again so that you can get the error. It's going to take a little while and it's going to give you some sort of an error. Okay, let's stop here. What if we try to ping 192.168.2.101? Obviously it's not going to work, but we need to figure out why. So ping 192.168.2.101. So let's go to our simulation mode again and hit enter over here. So the ICMP packet is initiated over here, it goes out, and then it goes out over here to this router, and you will see that over here the source is 192.168.1.101, the destination is 192.168.2.101, but this router doesn't know where 192.168.2.101 is. So what does it do? It says the routing table does not have a route to the destination IP address. All that means is I don't know where this destination IP address 192.168.2.101 is. I don't know. So what am I going to do? The device drops the packet. It drops the packet. I'm not going to forward it because I don't know where to forward it. The device sends back an ICMP host unreachable message. So a host unreachable message is going to be sent back. Okay, so let's send this back. Let's go back to real time so that you can see. You get the error message, destination host unreachable. Remember we had the timeout error? That was when we couldn't find anything. Now we got two destination host unreachable errors, which essentially means that we got to our gateway, but the gateway doesn't know how to send this packet out, which means if you get a destination host unreachable error, most likely your gateway is misconfigured. Okay, so let's go ahead and configure the gateway properly. For that, we go to the router and we go to this routing and static. So we are doing static routing right now. Later on, we're going to do dynamic routing as well. But what we're going to tell the router is, if you see any packet that you have to send out to 192.168.2.0 with a subnet mask of 255.255.255.255.0. If you're going to send out any packet to 192.168.2.0 with this subnet mask, which means anything on the 192.168.2 network, you're going to send it out to the next hop, which is this guy over here. Okay, so let me write this down and then explain. So what this says is, if you see a packet which you have to send to 192.168.2. whatever, you send it to 11.0.0.3 and let him or her or whatever, let it take care of that. Okay, so next hop means if you see a packet which has to go there, you send it on this wire and then forget about it. It's the responsibility then of this thing to take care of it. Okay, we add this over here and let's close this. Okay, now let's go ahead and also tell this router that if you see, so in the routing static, if you see a packet of 192.168.1.0 with the subnet mask of 255.255.255.0, you send it to 11.0.0.2. Okay, so we add this over here. Notice that it says 24 over here, even though we wrote 255.255.255.0, and they're the same thing. Okay, let's go ahead and close this. Let's make sure that we run this fast forward so that it works. Okay, so now we are going to go to the PC again, and we are going to go to the command prompt and enter our simulation mode, and we are going to say ping 192.168.2.101. Now the ICMP packet is going to go out. It goes to this, and this time this thing knows that the routing table finds a routing entry to the destination IP address, and it knows that it's supposed to send it out to 11.0.0.3. So it's going to send it out to 11.0.0.3. Okay, so the packet goes out to 11.0.0.3. Now when this guy sees over here, it's going to initiate the ARP because it does not know how to send this information to 192.168.2.01. This is old story, but you already know that once the ARP takes care of itself, then the packet is going to work out properly fine, as we did in the last lab. So let's go ahead over here, close this, and then let's go ahead and run this again. Now, this time you are able to send the packet to 192.168.2.101 and get the response back. Okay, so let's go to the simulation mode and click on this command prompt, and let's say ping 192.168.2.101, and this time very easily the packet goes out to the switch, to the router. The router knows that it has to send this packet to 11.0.0.3. It sends it there. This router, because it's on the same network as 192.168.2.101, it can send it out directly. ARP has been resolved, so it knows what the MAC address is. It goes out, the response comes back, it comes to router 2. Router 2 knows that this packet is headed over to 192.168.1.101, and in its router configuration, we have the information that if you have anything related to, so static over here, anything related to 192.168.1.0, you send it to 11.0.0.2, so it's going to send it out to 11.0.0.2, and that can send the response back to this guy over here. Okay, so everything is working fine. The issue is nobody knows about 192.168.3.0.1 at the moment. So if you try to ping 192.168.3.1.0.1, you're still going to get a destination host unreachable. In order to take care of that, you have to tell this router over here that if you have to send out anything to 192.168.3.10, sorry, so the whole network 255.255.255.0, the next hop is still going to be 11.0.0.3. So it says next hop. What do I do with it? I cannot send it out to this guy over here. Why? Because I don't know what the IP addresses over here are. I only know this guy. I'm only connected to this guy, so I can only send this as the next hop. Okay, so we add this over here, and in order to go over here, we need to also configure this guy. So let's go to the router 2. I'm doing this fast because we've already done this. Go to serial 0. Now here we have to give it a, so the next one. Here we have to give it a different network. So this is one network, this thing is another network, and this thing is a third network. So we have to give it a different network. So this is going to be 12.0.0.2. Give it the subnet mask of 255.0.0.0. Bring it back on. Close it. Go over here. Go to serial 0110. This now has to be on the same network as this. So this has to be 12.0.0.3. Give it the subnet mask. Bring it back on. And let's go ahead and add the nodes over here so that we remember. So 12.0.0.2, that's this guy, and 12.0.0.3, that's this guy. Okay, so this thing you have to do slowly in order to fully understand this. What we've said is that on router 1, if you want to send anything to 192.168.3.1, you just hand it over to 11.0.0.3. Let it take care of it. In here, we are going to say that if anything has to go to 192.168.3.0 with 255.255.255.0, router 2 is going to send it to 12.0.0.3. Okay, so let's see what the rules are. If a packet is initiated over here, it gets to this router and it's supposed to go to 192.168.0.3, 192.168.3. whatever. It's going to send it to this guy over here. Then it's the responsibility of this router. It's going to look at its routing table. So 192.168.3.0 should go to 12.0.0.3. So it's going to send it over here, and then, and then this guy is going to send it over here. We also need to go to router 3 and tell it that anything related to 192.168, so 192.168.2.1, so 2.0. Let's copy this, 255.255.255.0. If anything is to be sent out to 2.0, you should send it to 12.0.0.2. Okay. Also, if anything has to go out to 1.0, again, you just send it to 12.0.0.2 and let it take care of it. Okay. So now once this is done, let's fast forward so that everything is fine, and hopefully go over here, go to the command prompt, and now do ping 192.168.3.1, and now we should have this working. After a little while, obviously we might get a little bit of timeout, so there you go. Okay, so go to the simulation mode, go over here, and say the ping again, initiate the packet, and now it will be your task to watch the packet on each of its location and see what it's doing with the packet over here. It goes out over here because of the routing table of this guy. Then from here it goes to here because of the routing table of router 2. It goes down, and then the response comes back and we're done.